You know, everything around us seems solid, right? Bridges, airplanes, even the device you might be holding right now. But here's the thing, they all have a breaking point. So what's actually happening in those moments right before they fail? How can we possibly spot a tiny, invisible crack before it turns into a total catastrophe? Well, today we're going to dive into a breakthrough that basically lets us see the future of failure.
And look, this isn't just some academic thought experiment. Predicting exactly where a crack will grow is one of the single biggest challenges in all of engineering. And if you get it wrong, well, the consequences can be enormous. So the real question is, how do we get it right?
All right, here's how we're going to break it all down. First up, we'll talk about why this is such a high-stakes problem. Then, we'll look at the old, super expensive way people used to predict failure. After that, we'll get into a really cool new weather map approach, see how it holds up under testing, and check out its superpower for dealing with complex failures. And finally, we'll look at what this all means for a new era of safety.
So to kick things off, you've got to understand that pretty much every structure has tiny, microscopic flaws. The goal isn't to get rid of them completely, that's impossible, but to design things that can operate safely even with them. It's a concept called damage tolerance. But just picture a jet engine turbine blade spinning thousands of times a minute in extreme heat. An unpredictable crack there? Yeah, that's just not an option.
And that really gets to the heart of it. For decades, engineers have been pretty good at figuring out if a crack will grow under a certain amount of stress. But predicting its path, is it going to go straight? Will it turn? Will it just stop? Or will it suddenly split into two? That has been incredibly hard to figure out. And it's the path that determines whether a small flaw just stays a small flaw or becomes a complete catastrophic failure.
The classic method for tackling this is called computational fracture mechanics. It's a powerful tool, for sure, but it has a really fundamental limitation, especially when you're trying to model a crack that's on the move.
Okay, so here's the core issue with the old way. These models treat a crack like an infinitely sharp line. To do the math, the computer builds a grid, or a mesh, right around the tip of that crack. But, and this is the big but, the moment that crack moves even just a little bit, that whole grid is now useless. The computer literally has to stop, throw out the old map, and draw a brand new one from scratch. This constant remeshing is a massive computational headache. It's slow, it's expensive, and it makes modeling complex crack paths an absolute nightmare.
So what if? What if we just changed how we think about a crack entirely? Instead of seeing it as this sharp, single line, what if we pictured it as a continuous field of damage? Not like a switch flipping from fine to broken, but a smooth transition from healthy material to completely failed material. This is the big idea, the fundamental shift in thinking that unlocks a whole new way of doing things.
And this new approach has a name. It's called the phase field model. Probably the best way to wrap your head around it is to imagine a weather map. But instead of tracking things like air pressure, it's tracking the health of the material itself. So the whole model works using this key variable called the phase indicator, or phi. Just think of it like a health meter for every single point inside the material. If phi equals 1, the material is perfect, totally pristine. If phi equals 0, it's completely broken, that's the crack. And everything in between, 0.99 down to 0.01, that represents some state of partial damage. And this is what that looks like. It's pretty cool, right? Instead of that sharp line, the crack is now this diffuse region. The red area here, that's the perfectly intact material where phi is 1. The dark blue, that's the fully formed crack where phi is 0. And that beautiful gradient of color in between, that's the damage zone. It's just like a weather map showing a smooth change from high to low pressure. The crack's path is now just the path of this evolving 0 phi weather front. And the best part, no remeshing needed at all.
Okay, it's a brilliant idea in theory. It's elegant. But for engineers, the only thing that really matters is, does it actually work in the real world? So the huge question is, do the predictions from this new phase field model actually line up with the trusted, proven results from the classic methods? Does it get the numbers right?
Well, the data really speaks for itself here. The researchers tested the model on some standard, textbook crack problems. This first column shows the accepted value, the stress needed to make a crack grow, calculated the old way. The next two columns, those are the predictions from the new phase field model. And just look at those numbers. We're talking 22.92 versus 23, or 14.93 versus 14. I mean, the agreement is just incredibly strong.
And this graph shows it even more clearly. This is a plot of the stress right at the very tip of the crack. The green line, that's the classic textbook solution. The blue line is the prediction from our new phase field model. You can barely see the green line because they are almost perfectly on top of each other.
This is fantastic proof that the new model isn't just some clever idea. It is quantitatively, measurably accurate.
So, we've established the model is accurate for simple cases. That's great. But its real superpower, that comes out when things get complicated. When we need to predict those unpredictable behaviors that the old models just choked on.
And this is the amazing part. Behaviors like a crack turning or suddenly splitting into two, they just emerge naturally from the model's equations. The engineers don't have to tell it, hey, turn here, or okay, split now. The model, just by letting that weather map of damage evolve, predicts these complex real-world failure paths all on its own. This was something that was just extremely difficult, if not totally impossible to do with the older methods.
And hey, you don't have to take my word for it. The researchers say it themselves right in the paper. The classic approach, which they call LEFM, runs into serious technical and conceptual difficulties when it tries to predict crack branching. The fact that the phase field model just handles it with no extra fuss, that's a genuine game changer.
So, let's tie all this together. What we have here is a new model that's way more efficient, it's been proven to be accurate, and it can predict complex failures that were pretty much off limits before. So what does this actually mean for the future of engineering and for all of our safety?
So here are the big takeaways. First, because it gets rid of that whole remeshing problem, it's faster and cheaper to run these simulations. It accurately predicts not just when a crack will start, but also when it might stop, a super important concept called crack arrest. As we just saw, it handles tricky paths like turning and branching like it's no big deal. And all of this together lets engineers create much more sophisticated, damage-tolerant designs, which means building safer, more reliable, and more efficient structures for all of us.
And this all brings us to one last really powerful thought. For so long, engineering has been focused on predicting failure. But if we can now simulate exactly how cracks are going to behave before we even build a thing, can we start to design materials that actively guide cracks or even stop them in their tracks? What does the world look like when we shift from just predicting failure to actively engineering resilience? That is the exciting new frontier that this model opens up.